Now we're going to see the formula for the listening to a sound wave that is moving towards the listener. Also, if the listener is moving or away from the listener and the listener could also be moving. So here we have the source of the sound waves. He is stationary, more or less. Here we have the person that is listening. So if we do that, the person goes towards the source and the source is also moving, then we will see that the pitch that the listener is going to hear is higher because the frequency is higher, and when they are apart, it would be a lower frequency, so lower pitch. So this is combination of the previous two videos. So when we have that the source is moving and the listener is stationary, we see that the wavelength is changing. If the source is moving towards the listener, the wavelength is coming shorter. So it's the wavelength actually of the wave minus the distance advanced by the source, that is delta lambda. We have that lambda is the velocity of the or let's say that the frequency of the source that is emitting the sound waves is the velocity of the propagation of the sound divided by lambda, and the lambda, so here would be the velocity divided by the frequency that are emitted this source. Now if we have that the source is moving, we have that at a interval t, the wave has advanced a distance lambda of b over f, or b times the period, that is this t, and the source has advanced a distance delta lambda of the velocity of the source moving times this time interval, that is the same as this divided by the frequency. So we have that is if the listener is stationary, this is as we saw on the previous video. We have that the velocity at which the crest of the sound wave is hitting the listener would be the velocity divided by the lambda. This will give us the frequency. This is the formula, but here lambda is this. So lambda is actually velocity divided by frequency minus velocity of the source divided by the frequency. So we have velocity divided by velocity f minus velocity s, all of this over f. This will be equal to the frequency of the listener. Then I can multiply everything by f. I would have v divided by v f minus v s, sorry, v like this, times f, and then we can do manipulations, etc. But now the issue is, this is if the source is coming towards the listener. If the source is going away from the listener, then the wavelength, or here's another person, the wavelength is getting larger, and so we will have velocity divided by v plus v sub s. We saw this on the previous video. Now the issue is if the listener is also moving. So if they are both moving, then we have that the velocity at which they are approaching is not only the velocity of the sound wave and the source that is moving, but it's also the velocity of the person. So here, instead of having that the frequency of the listener is just the velocity of the sound wave divided by our new wavelength, that this wavelength is lambda minus this delta lambda. Here we don't have just the velocity of the source of the wave moving, we also have the individual moving. So we have to add here the velocity of the listener if they are both coming together. So actually here we will have the velocity plus the velocity sub lambda, so the listener divided by lambda, that is this v minus v sub s all by f, or the frequency times the velocity of the sound wave plus the velocity of the listener divided by the velocity minus the velocity of the source. And if now they are both moving apart, so we will use this equation now, because this is when the wavelengths are coming larger because it's going away from the individual, or as in this case. But also if the listener is going away of the source, then we also need to count this movement of the individual, and so the velocity at which they are coming away is the velocity, and this velocity is negative. So here will be minus the velocity of the listener. Or you can think it as plus the velocity of the listener, but the velocity of the listener in this case would be negative. So these are the formulas for the frequency that would be heard by a listener if both the listener and the source of sound waves are moving. And if we take that the listener is at rest, then this visible listener would be 0, and we have exactly the same equation as if the individual were not moving, and so it's just the source that is moving and the individual is at rest.